Hello friends, today we will discuss resistance to traction. And when I say resistance to traction, it means basically when a train moves on the track, it experiences certain forces which oppose the movement of the train. And these are resistances. The first in the category is resistance due to friction. Now this resistance is composed of three components, that is journal friction, the internal friction and the rolling friction. Journal friction is the inertia of the locomotive or wagon itself, and it depends upon the type of lubricant used, it depends upon the age of the rolling stock, and it depends upon temperature also and some other factors. The internal friction is because of movement of internal parts of a locomotive or a wagon, and rolling friction is the friction between wheel and the rail. Now this journal friction is similar to the force of inertia. The total resistance due to friction is evaluated as 1.6 kg per ton weight of the train. That is empirical equation, because exact evaluation of this friction or resistance is difficult, and therefore in Indian Railways it is assumed 0.0016 W is the weight of the train. The second resistance is due to track irregularity. Due to track irregularities. Now it can be because of poor maintenance of the track, and even if a newly laid track also, see when a train moves, the rail is supported on a number of sleepers, and these sleepers are embedded in the ballast, and when a wheel comes here, it creates a deflection in the track. Rail gets deflected, and because of this deflection, a wave is created in the rail. The portion which is beyond the wheel is slightly lifted, and the portion which is behind the wheel is also slightly lifted, and the part of the rail which is just below the wheel is deflected. Now this amount of deflection will depend upon several factors. It will depend upon the rail section, wheel load, condition of the track, how much support is provided by the sleepers, and how good is the fitting of the track. And it will also depend upon the speed of the train. Now because of this deflection, when the wheel moves in forward direction, then it tries to push this rail back, and then the reverse happens. When the wheel comes here, now this part is deflected and this wave moves forward. So in fact, the movement of the wheel is continuously uphill, and that is the resistance due to track irregularity. And this resistance, as I told you, it depends upon the weight and it depends upon the speed, and it is taken as R2 is equal to 8 into 10 to the power minus 5 into W into V. W is the weight of the train in tons, V is the speed in kilometer per hour. That is resistance due to track irregularities or due to wave action. Then third is resistance due to wind. Resistance due to wind. Now this is because of exposed area. When the train moves, certain force is offered or certain resistance is offered by the wind, and that depends upon the exposed area. Total wind resistance is equal to the head resistance, the side resistance and the tail resistance. And it also depends upon the speed of the wind. The speed of the wind and also the angle of the incidence of the wind. And the sum of these three resistances which I told you, head resistance, the tail resistance and the side resistance is maximum when the wind blows at an angle of, when the wind blows at an angle of 60 degree to the direction of the movement of the train. And it depends upon the exposed area, and therefore the equation which is used to calculate this resistance is, let us say R3 is 0.00017 AV square. Here is the exposed area in meter square and V is the speed in kilometer per hour, R3 resistance due to wind. And because in case of railways, the size or dimensions of the wagons and the coaches, the locomotive are more or less standardized, and therefore rather than using area which is difficult to measure, we take the weight of the train, and it is taken as 6 into 10 to the power minus 7 W into V square, where W is the weight of the train, R3 is the resistance due to wind, V is speed in kilometer per hour. That is the resistance due to wind. The fourth is resistance due to gradient. Resistance due to gradient is present only when there is a positive gradient. Then let us say this angle is theta, O, A, B. The weight of the train acts downward, and this is, let's say, W, force applied by the engine in forward direction, and if you divide this into two components perpendicular to the track, that is W cos theta and W sin theta. Now this is the extra force because of gravity, W sin theta. And F is, or you can say R4 is W sin theta. W is the weight of the train. And theta is small, and therefore if you take theta equal to AB upon OA, and because theta is small, so OA can be taken as OB, and that becomes W into AB, that is the rise in length OB. That is the gradient, 1 in n. If this is 1, how much is this one? That is how we express the gradients. So it is W into G. G is either you take in fraction or in 1 in n. This is the resistance due to gradient, and it is present only when the train moves on upgrade, on vertical curve. The next one is resistance due to curvature. This resistance is prominent only when the track is laid on a horizontal curve. And this resistance is mainly because of three reasons. When the track is laid on a horizontal curve, then movement of the train, the force applied by the engine is always in forward direction, and therefore the train or the wheels tend to move in forward direction until the wheel flange of outer wheel strikes the side of the outer wheel, and then it moves continuously rubbing the side of the wheel. And if you take a horizontal curve, then the length of outer rail is more than the length of inner rail, and that amount, let us say this is L1, this is L2, or same central angle, then the amount of or the difference between the length of two rails will be L1 minus L2, and this will be, that is the radius of the outer curve R1 and the radius of the inner curve R2, inner rail. So it will be R2 minus R1 into theta. And R2 minus R1 is the gauge of the track. So this is gauge into theta. Now this is the difference in length of two rails on a horizontal curve. And because of rigidity of the wheel base, wheels cannot move independently, and therefore the outer wheels have to travel a larger distance than the inner wheel. And because of coning of wheels, taking advantage of some advantage of coning of wheels, the outer wheel tries to move outward, so that diameter of this wheel increases slightly. But as we discussed in the case of coning of wheels, the full advantage of coning of wheels is not achieved on horizontal curve because of this rigidity of the wheel base, and therefore when it moves outward, the inner axle, the rear axle will move inward. So this wheel now tending to derail, and similarly this wheel tending to derail. So the resistance due to curvature is mainly because of three reasons. Number one, because of this transverse slip of the wheel, because of longitudinal slip of the wheel, because this outer wheel has to travel a larger distance, and therefore it tries to slip on the rails. Skidding and slipping is very prominent on horizontal curves. And third is because of rigidity of the wheel base. Now this is the total force or the resistance due to curvature, and this resistance depends upon several factors. Certain observations based on experience are like this, that this resistance due to curvature depends upon the speed. R phi depends upon the speed of the movement. It is at high speed and low speed. It depends upon the central angle theta, but it does not depend upon the radius of the curve. That means that there are two curves with same central angle theta. One is having a very large radius and one another having small radius. The resistance will be same, because here the resistance is the function of the slip, amount of slip. The amount of slip is g into theta. It depends upon the gauge, naturally. It is less for new rails and more for old rails. It depends upon the weight of the train also, but the length of the train does not have significant effect on the resistance due to curvature. And because of all these factors, the equation which is used to calculate resistance due to curvature is like this, that R5 is 0.0004 WT, 0003 WT, or 0.0002 WT for broad gauge, for meter gauge, for narrow gauge. So W8 is the weight of the train in tons, and D here is the degree of the curve. D is degree of the curve. Degree of the curve. So that is how we calculate resistance due to curvature. So these are 5 prominent resistances which are offered to the movement of a train. But when the train accelerates, and if it is required to increase the speed of the train from V1 to V2 in a length L or in a time T, then extra force is required. Resistance due to R6, you can say, resistance due to acceleration. When the speed of the train is increased from V1 to V2 in a length L, then you can calculate the amount of force required, power required, by equating the change in kinetic energy equal to the work done. So if R6 is the RC resistance or the force required, then this R6 into L is the work done by the engine, and the kinetic energy is half m v square, that is half m v2 square minus v1 square. Here v1 and v2 are meter per second. This mass can be kept equal to W upon G, that is the weight of the train and acceleration due to gravity. Then R6 will be equal to 1 by 2 W upon G and V2 square minus V1 square. If you put value of G here and take speed in kilometer per hour, then this equation becomes 4W into V2 square minus V1 square. Now V1 and V2, they are now in kilometer per hour. So R6 into L. Value of work done is equal to kinetic energy, change in kinetic energy, and therefore R6 will be equal to 4W upon L into V2 square minus V1 square. Now this is the force required for motion of translation. That is how the equations have been derived. But when you provide rotatory motion, the force will be sufficient to provide rotatory motion to the wheels as well as motion of translation. And therefore that force is slightly more than this. And if you increase this by just 5%, the total distance to or total force is 4.2 W upon L into V2 square minus V1 square. Now here W is in tons. V1 and V2, they are in kilometer per hour. L is in meter and unit of R6 is in kg. Now similarly, if you know the time rather than its length, if you know the time, the speed is increased from V1 to V2 in time t, then this equation would be R6.028 into W8 upon W into V2 minus V1 upon. Here V1 and V2 are in kilometer per hour, time is in second, but the unit of R6 is same as unit of W. But here unit of R6 is in kg and W is in tons. Now this extra force is required only when train is to accelerate from speed V1 to speed V2, either in length or in a given time. Otherwise, the power of the locomotive should be sufficient to counter the first 5 resistances. That is R1 plus R2 plus R3 plus R4 plus R5. That should be equal to the holding capacity or power of the locomotive, holding capacity of the locomotive. R1, R2, R3 resistance due to friction, resistance due to track irregularities or wave action, resistance due to wind, resistance due to gravity, resistance due to curvature. We should remember that when a train moves from position A, from station A to station B, there will always be some track, a horizontal curve, there will always be a vertical curve. And therefore, R4 and R5 should be considered based on the degree of the curve on the track and based on the steepest gradient. So that is how we calculate total resistances, and for a given power of the locomotive, this equation will be that volume capacity is equal to 0.016 W plus W, 0.0002 WT depending upon the gauge. Now, if you know the volume capacity, this equation can be used to determine the weight of the train for a given speed or the speed of the train, maximum speed of the train for a given weight of the train. So that is how it controls the weight and speed of the train. So friends, thank you very much for watching this video. We have discussed resistance to traction, and if you have any question, you can write in the